Bismillahirrahmanirrahim. In this course module, we will talk about one of the important concepts of linear algebra, that is matrix vector product. That how do we multiply a matrix and a vector? What is the interpretation of matrix vector product? What are the application examples of matrix vector product? I feel that if you understand the action of matrix on vector, or if you understand this matrix vector product, this is the essence of linear algebra. And later we will talk about matrix product that generalizes matrix vector product. Okay, let's start with matrix vector product. We define a matrix vector product for a matrix A uh, with m number of rows and n number of columns, and we take a vector x and that has n number of rows and one columns, so it's a vector of size x. And we define the multiplication between a matrix A and vector x when number of columns of A n is equal to the size of this vector n. So we say the condition of the multiplication is that we require number of columns of A equals the size of x. And we define this multiplication, say we take y is equal to ax. So when you multiply a and x, what you obtain is y. And the number of elements in the y is the number of rows in A. So y belongs to Rm. So if we express this in the components of y, a and x, so what we say is we have y here that belongs to Rm, and we have a matrix A, and we have a vector x. So y belongs to Rm. So this y, hang on. So this y belongs to Rm, and A belongs to Rm cross n, and x belongs to Rn. Right? And the way this multiplication is defined, that given A and x, how do you get y? And that is given by this relationship. So you want to find yi. So this yi is given by ai1 times x1 plus ai2 x2 plus ain ai3 x3 and so on and so forth ain xn. So to find the ith entry of the product y, so what you do, so you take ai1, ai2, ai3 and so on and so forth ain. So these are the elements in fact at the ith row of the A matrix, and you multiply ai1 with x1, ai2 with x2 and so on and so forth, right? So that is simply given by, I would say, the inner product between ith row of A and a vector x. That's how we define the product of a matrix and a vector, right? For example, this y2, so y2 would be given by inner product between this second row and this vector, right? So y2 would be a21 x1 plus a22 x2, so on and so forth, a2 plus a2n xn. So that's how we define matrix vector product. Let me also explain with one example. So say we take a matrix A and a vector x. So this is A and this is x. A has 2 number of rows, 3 number of columns, so A belongs to R2 cross 3, and x belongs to R3. So the number of columns of A are same as size of x, so this multiplication is compatible. So we can multiply A and x, that we take the inner product of the first row and the vector x, second row and the vector x, and what you obtain is y that belongs to R2. So this is y given by A times x. Let me also explain this interpretation of matrix vector product. So that's how we defined the matrix vector product. So if we want to interpret this matrix vector product in terms of rows of the matrix A, so let me stack the rows of this matrix A in this form. So I use R1 to denote the first row of the matrix A, R2 to denote the second row of the matrix A, and so on and so forth. So this matrix has m number of rows, so we have m number of rows here, where each Ri belongs to Rn, because number of columns of A are number of columns of A is Rn. And when we multiply this with vector x, so what we obtain is y. So y is equal to ax. So this is A represented in terms of rows of A, x, and this is y. And what we said earlier, that, and you can see here that yi is simply given by Ri transpose x, or inner product of Ri with x. Or we can say ith entry of the product is simply inner product between ith row of the matrix and vector, or ith row of the product is the projection of the vector on ith row of the matrix A. Let's also talk about interpretation of matrix vector product in terms of columns of a matrix. Similarly, so I'm going to use the notation. I'm going to define each column with each column of the matrix with a different vector. Say A1 denotes the first column of the vector, A2 denotes second column of the vector, and if I stack all of these vectors, so I get this representation of matrix A, with each AI belongs to Rm, and when we multiply this with the vector x, we obtain the product y is equal to ax. So this is x and this is y, so y is equal to ax. And if you see this interpretation, so what you get is, in fact, this is this, that y as x1 a1 plus x2 a2, so on and so forth, plus xn an. How do you interpret this? How do you read this? This is nothing but just a linear combination of columns of A. So here a1 a2 an are columns of A, x1 x2 xn are scalars, and these scalars represent the entries of a vector x. So we can say, so y is equal to ax is a linear combination of the columns of A, where the coefficients of the linear combination are given by entries of the vector x. So this is another interpretation of the matrix vector product in terms of columns of a matrix. Before we talk about more interpretations of matrix vector product, let's talk about some applications in which we use this matrix vector product. We start with this application example. Say we have a 200 times 70 matrix that represents the quantity of 70 products stocked in 200 warehouses. We can say we have a matrix A. Here we take m is equal to 200 and n is equal to, so we have 70 products and 200 warehouses. So what does quantity 21 denote? So A21 denotes the quantity of the first product in the second warehouse, and similarly AMN, so this term AMN, so this describes the quantity of the nth product, the 70th product in the 200 warehouse. So assume that we know the value of each product, And what we want is we want to determine the value of the products, the value of all the products in each warehouse. So what is given? So we know the value of the first product, the second product, and the seventh product. And let me concatenate all of these values in a vector. Say x1, x2, x70, right? And what is xi? Value of ith product. And what we want is we want to find out value of all the products for each warehouse, right? So we can say we want to determine value of all products. How should we compute it? So for example, for the second warehouse, what do we want to determine? So we want to determine a21 times x1 plus a22 times x2, and so on and so forth. And that is in fact matrix vector product. We can say if we take y is equal to ax, so this y would belongs to R200, and each element of the y quantifies the value of all the products in that warehouse. Say y3 would denotes the value of all the products in the third warehouse, and so on and so forth. We talk about one more example. Say in machine learning, we have a problem in which we want to determine whether the person is smiling or not, or we want to detect the mood of the person given the photo, right? So the problem is referred to as a problem of feature matrix and weight vector. Say you have hundreds of photos, and for each photo you compute the features, right? Say you have a matrix A in which, so along rows, say you have data for say photo 1, photo 2, and so on and so forth, and say you have 1000 images, and for each image say you compute 70 features. So along columns you have the features. For example, this, if I have a quantity a21, so a21 describes and the first feature of the second photo, and similarly say a43 would describe the third feature of the fourth photo, and so on and so forth. So a belongs to R1000 times 70, and what we want is we want to obtain score for each of the photo. So we want to give different weights to each feature, and we want to compute the score for each photo. Let's say we stack the weights for each of the feature in a vector W, and say W1 is the weight we want to assign to the first feature of each photo, W2 is the second weight for the second feature, and so on and so forth. So this should be W70, and we want to compute score for all of the photos. Or so what do? So we want to simply multiply A with W, and let's say what we get is Y. So Y belongs to R1000. So what does Y1 quantify? Y1 quantifies the score of the first photo, Y7 quantifies the score of the seventh photo, and so on and so forth. Let me talk about two more examples. expansion in a basis. Uh, we are in Rn, and we assume that we have a1, a2, an, n number of linearly independent vectors that represent basis of Rn. So we know that we can represent any vector b that belongs to Rn as a linear combination of these n number of linearly independent vectors. So, and we represent b1 a1 plus beta 2 a2 plus beta n an, and where these beta 1 beta 2 beta n quantifies the contribution of bases in b. If we stack all of these a1 a2 an in a matrix a, so a1 a2 an represents columns of a, and if I stack all of these betas in a vector beta 1 beta 2 beta n, so I can represent b is equal to a times this vector, let me call it beta. So we can say this is the representation of a vector in its bases which are stacked in a matrix A. This is a matrix vector product. Using matrix vector product, we can also check linear independence of columns or linear dependence of columns. So we have vectors which we stack in a matrix A. So columns of the matrix A are linearly dependent if ax is equal to 0, say for some x which is not equal to 0. So this is the case when we have linear dependence between columns, because we know that ax represents a linear combination of columns of A. So ax is x1 a1 plus x2 a2 and so on and so forth. So ax is equal to 0 for some x is not equal to 0 means there is a linear dependence between the columns of A. If ax is equal to 0 and implies x is equal to 0, for x is equal to 0, so only then we have linear independence between columns of A. These were a couple of examples to demonstrate the use of matrix vector product. Let me talk about some more interpretation of this matrix vector product. We can see this matrix vector product as a linear transformation, or we can interpret as input-output system. So how do we define this matrix vector product? Say we have y is equal to ax, and we know that this multiplication is compatible if the number of columns of A is same as size of x, and what you get is y as a product of A and x, and y, the size of y is the same as number of rows of A. So we can say this matrix A is acting on a vector x that belongs to Rn, and it returns you a vector or a point that belongs to Rm. So we can say this is a mapping from Rn to Rm. Or if we see it as, if we interpret it as input output system, so let me represent using this system level diagram. Say we have a matrix A that defines this system, and this system has some input. The arrow pointing inwards is the input, and the arrow pointing outwards is the output. So here the input is x belongs to Rn, and the output is y that belongs to Rm, and the relationship between output and input is linear, and that is given by y is equal to ax. Okay, so why do we call it linear? In fact, linearity is a very broad topic. Let me explain here very briefly as a byproduct of this module. So why do we call this transformation of x to y through a as linear? Okay, so that is due to two properties that forms the basis of linearity. The first one is scaling. That simply says if you multiply x by a scalar alpha and you pass this alpha x through a system, if output gets scaled by the same value, we say a system satisfies scaling property or homogeneity property. So if you get here alpha y, and when input is alpha x, we say a system is homogeneous or it satisfies scaling property. And here we know that if we have this input output relationship and if a acts on alpha x, so by definition of scaling on vectors, what you get here is alpha times a of x, and that is equal to alpha times y. So this system given here satisfies scaling property. Okay, so scaling is okay. We say the system satisfies scaling property. The second property which we should check for linearity is additivity, or we also call it superposition. That simply says if you have one input x and you get output y, and if you say input u that belongs to Rn, and what you obtain is say v that belongs to Rm, and if I input a sum of these two, x plus u, and if I get y plus v, that means if you add two inputs, the output gets added as well. And this property is called additivity or superposition. If system satisfies both additivity and scaling, so we say a system is linear. And in fact, this is true for any mapping, any functional mapping from one space to another space, or from one domain to another domain. So this all can be captured in just one equation. Say if we have a function that maps from Rn to Rm. So here this function is simply a matrix A, and that multiply with a vector x input. So we say this function is linear if a function of alpha x plus beta u is equal to alpha times f of x plus beta times f of u. So this single equation captures both additivity and scaling, right? So linearity is defined by two properties, scaling and additivity, which we also refer to as superposition. So this is the interpretation of a matrix vector product as input output system, or as linear transformation. Let's take a couple of examples to understand this input output system interpretation. See, we have this input output system interpretation, and let me take one example. Say I take this as a matrix A. So what is n and what is m here? N is 3, m is 2. We can say this system maps from R3 to R3. So that means when you define A times x, so if I take this x what do I get? A times x. So what's the interpretation? So what is the system doing? If you take any x, what do you get here? That is x1, x2 multiplied by 10, you get 10x2, and what you get is negative x3. So we say when A is a diagonal matrix, a linear transformation is simply scaling of different components, and the amount of scaling is defined by the diagonal entry. Say x1 is scaled by 1, x2 is scaled by 10, and x3 is scaled by -1. So you give any vector x, and what you obtain is x1, 10, x2 minus x3 as different components of the vector y. So this is y here, right? Say for this particular example, if I give this input, so 1 minus 3, 5. So what do I get? So if this is x and this input to a system A, it's defined by A, and what you get is 1 minus 30 minus 5. Right? So a diagonal matrix that simply represents scaling of different components. So let's also take one more example. Say we take this matrix A. So what does this system represent? So for this A, the system maps from R3 to R2 because we have 2 rows and 3 columns of a matrix. This matrix acts on X that belongs to R3, and what you get is a vector in R2. Right? So okay, if this matrix X multiplied with this matrix A, so what do you get? Y, and this Y belongs to R2. So A times X would be, if you follow the definition of a matrix vector product, so 1 times x1 plus 1 times x2 plus 0 times x3. So what you get is x1 plus x2, and you get the third component. How do you interpret this? So say A is a system that takes 3 inputs and it returns you 2 outputs. The first output is the sum of first 2 inputs, and the second output is the third input. So that's how you interpret this. Right? And again for a similar input, 1 minus 3, 5. So if this is x and you give this to a system A, what you get is 1 minus 3 minus 2 and 5 that belongs to R2, and this is y. So let's take one more example. How do you see this matrix A? So this matrix has 4 rows, 4 columns. You can say the system interpretation is that it maps from R4 to R4. So what, say if I take this x, what do you get? So A times x would be x4, x3, third row x2, and x1. So what is this system doing in fact? So this is just reversing the order of the input, right? So x4 is mapped, so x4 gets replaced first x3, x2, and x1, right? So we can say the system has a special name, we call it reverser. So in fact, this reverser is a special form of a matrix which we call permutation matrix. Let me also define what do we mean by a permutation matrix. Okay, if you see this matrix A here, so this matrix A has some special form, right? So it has one element, one non-zero element that is equal to 1 per row, and one non-zero element 1 per column, right? So if any matrix that satisfies this property is called permutation matrix. So for example, if I swap the order of these two second and third column, so what will be the consequence of the output? So x2 and x3 would be swapped, right? So and if you arrange these columns in different orders, so the output would be input, components of the input arranged in different order. And that's why so we in general we define a permutation matrix, say we denote with P, and that's a square matrix that belongs to R n cross n, right? So it's a 0 1 element, so it's a 0 1 matrix with one element which is non-zero per row, and we only have one element per column, and columns and rows can be arranged in different orders, but it must satisfy these two properties. So it's Rn cross n, and each entry, say Pij, each entry can be either 0 or 1. So this is a permutation matrix. So a permutation matrix would simply change the order of components of the input. This was all about matrix vector multiplication. So we define how do we multiply matrix with a vector, under what conditions, what are the different interpretations of matrix vector product in terms of columns of a matrix, in terms of rows of a matrix, as linear transformation, or this input output system interpretation. We have also reviewed some examples in which we used this matrix vector product. So now we're going to define what do we mean by matrix multiplication. We take two matrices. We take a matrix A that belongs to R m cross n, and we take another matrix B that belongs to R n cross B. So we define the multiplication of A and B as A times B, and say what we get is matrix C as a result of multiplication of a matrix A and matrix B. So let me explain the entries of this C and relate those entries with the entries of A and B. Right? So first we note that this multiplication is compatible only when the number of columns in A is equal to the number of rows in B. We say this multiplication is compatible only when this condition holds, right? So and size of C, what you obtain as a by multiplying A and B, so this C belongs to R m cross B. So we can say let me write the dimension of m cross n, the dimension of the first matrix, and you multiply with a matrix B, dimension is n cross B. A multiplication of these two matrices is compatible in an order A times B when this dimension matches. So this, if this is same as this, the multiplication is compatible, and when you multiply A B, so what you get is a matrix of size m times p. So if I represent these matrices in expanded form, let's say we have this C with m number of rows and p number of columns, and which we obtain by multiplying A with B, right? Now we're going to relate the entries of C to the entries of A and B. Say, okay, let me first define mathematically. So C is equal to AB. This simply implies that the entry at ith row and jth column of the matrix C would be given by aik. So here I is fixed and your summation is over k times bkj. Here k is fixed and j is fixed and summation is over k. Or we can simply say cij is the inner product between say ith row of A and jth column of, okay, let me write more clearly. Okay, maybe let me explain this. Say we take ith row of A and jth column of B. So this is the entry of the product C at ith row and jth column, right? Or we can simply say if we want to obtain this C21, so this is simply given by the inner product between second row of A and the first column of B. So that's how you obtain C21. So C21 is A21 times B11 plus A22 times B21 and so on and so forth, plus A2n times Bn1. Right? You can also interpret this by representing this matrix B as in a column representation. Say B1 represents the first column of matrix B and B2 represents second column of matrix B, and let's say this is the representation of a matrix B. So what you obtain is, so if I multiply this matrix A with B1, so what do I get? I get the first column of this matrix C. If I multiply this matrix with the second column of the matrix B, what I obtain is the second column of matrix C. Or we can say this matrix multiplication generalizes a matrix vector product. So you have matrix times one vector, you obtain the first column. To multiply matrix with the second column, you obtain second column of the output, and so on and so forth. Let's talk about some of the properties of this matrix multiplication. So this multiplication of two matrices is not commutative. So A times B is not same as B times A in general. So there are some exceptions, but in general, matrix multiplication is not commutative. However, the multiplication is associative, and when we have multiple matrices in a product form, so we don't use brackets to separate the order of multiplication. Furthermore, the matrix multiplication with scalar is also associative. We also note that if you have a product of matrices and you take a transpose, that is same as if you take transpose first and change the order of the multiplication. So AB whole transpose is same as B transpose A transpose. We also note the multiplication of block matrices. So The block matrices are multiplied in a standard way, the way we define multiplication of matrices. So it simply needs that. So we require dimension compatibility only. So we assume that the dimension the dimensions are compatible for these block matrices. That simply means if we want to multiply a and w, so we want number of columns in a should be same as number of rows in w. Before we close, we also look at a couple of examples of matrix multiplication. Say we take two matrices a and b. So matrix a has a size 2 cross 3, and matrix b has a size or 3 cross 2. So number of columns in a is 3, the number of rows in b is 3. So multiplication is compatible, and when you multiply these two, so what you get is c. So what about the first entry of c? That will be given by minus 1.5 times minus 1 plus 3 times 0 plus 2 times 1. So you simply take inner product of the first row of a with the first column of b, and if you continue this, so what you get is this c. So for example, this minus 1 is simply given by taking inner product of second row with the first column. So 1 times minus 1 is minus 1 times 0 is 0, 0 times 1 is 0, and when you add these all, you get minus 1. Maybe we also talk about what do we mean by outer product of vectors using matrix multiplication notation. Okay, say if you have two vectors, say a that belongs to Rn and b that also belongs to Rn, so we define their outer product as a b transpose. So what's the dimension of a? N cross 1. And what's the dimension of b transpose? 1 cross n. And when you multiply a with b transpose, what do you get? A matrix of size n cross n with entries given by this. So a b transpose is a1 b1, a1 b2, a1 bn, and so on and so forth. So each the product of each entry of the matrix of the vector a with each entry of the vector b. So this is called outer product of two vectors a b belongs to Rn. So we also define what do we mean by gram matrix or gram matrix product. Say if I have a matrix A that belongs to R m cross n, so we define a gram matrix and denoted by G, that is simply a product of A transpose with itself. And what you get is, so A transpose would be a matrix of size n cross m is m cross n, and what you get is a matrix of size n cross n, and that will be simply given by this matrix, which we call gram matrix. So what are the entries of gram matrix? So the first entry is the inner product of the first column of A with the first column, and in fact if I call this G matrix, and so Gij, so this entry would be AI transpose times Aj, where AI and Aj represents ith and jth columns of a matrix A respectively. That was all for today. We will continue in the next module. Thank you very much.